Hello there, welcome to our today's science lesson. The topic for the day being the periodic table. I know as you have been going through science lessons in various ways, you have been hearing probably this name, periodic table. You also heard the name periodic table in our previous science lessons, particularly to do with the chemistry part, where we were looking at some scientists on how they were developing the atomic theory. You realize that there's a very big scientist who was the first one to look at this case of the periodic table, and that is Dmitry Mendeleev. In early years of 17th century, that is in 1869, where he attempted to arrange elements. That is Dmitry Mendeleev in 1869. He attempted to arrange elements in order of their atomic masses and characteristics. Why this scientist by the name Dmitry Mendeleev in 1869 did this was to assist us, the world, understand these elements that were so many in terms of how they behave, their characteristics, their similarities, their differences, categorizing them, so that because of the so many different uses that were being gotten out of these elements, it will be easier for others also to know exactly what to look for when they want to do one or two things. So Mendeleev came in to arrange these elements in an orderly manner, that is in vertical and horizontal lines, so that you categorize these elements as per how they behave. Those that have similar characteristics be put in one particular point, and those that are different be obviously placed in a different category. So he came up with, which is still being done up to today, he came up with a table where you find that you will have horizontal lines, and you will also have vertical, horizontal columns and vertical columns. Where you have the vertical columns, they will be carrying elements that have the same characteristic. Vertical columns will be carrying same characteristics, chemical properties, chemical characteristics. If element A and B are showing some similar way of reacting, then we can say they have the same chemical characteristics, chemical properties. So such elements will be placed in the same vertical column. But remember, we are talking about two different elements, 3, 4, and so on. So which one will be placed in the first part and which one will be placed in the last part? So he came in also to look at the number of electrons in the outermost energy level, or in the outermost orbit of those electrons. Remember, though we shall cover this one in detail in our coming science lessons, but just a highlight of it so that you can get the clear picture here. Atoms have a center part, which is the nuclei, which carries protons and neutrons. You remember in 1932, James Chadwick discovered the neutrons, because previously only the protons had been known. So in 1932, a scientist by the name James Chadwick discovered another particle, subatomic particle, which is a neutron, and it is normally found in the center of an atom. So the proton and neutron being responsible for the mass of an atom. But around these proton and neutron in the nucleus, we have the electrons which orbit around what we call energy levels or orbits. Energy levels or orbits around the nucleus. So in the outermost orbit or in the outermost energy level, I'm using the two because depending on the book you may find, you can easily find a book talking about energy levels or another one talking about orbits. They are the same. Orbits were commonly used by John Dalton when he was coming up with his atomic theory, which is helpful up to now. So he used the term orbits, but you will find that in some books we use energy levels because these electrons that are found in these orbits, they carry different amount of energies. That's the name energy levels. So in the outermost orbit, if you find an element has only maybe 2 electrons and another one maybe has in the outermost orbit has maybe 4 electrons, these two will not be placed at the same point in the periodic table. They will be placed at different positions. But remember, we have said if they have the same way of reacting, the same route of reaction, then we shall categorize them into one vertical group, which we call a group. That is a group of particular elements that are reacting in a particular way. The only difference here is they are carrying a different number of electrons in the outermost energy level or in the outermost orbit. Because of this, those that will be carrying 2 will be placed in horizontal column 2. Those that will be carrying 1, horizontal column 1. Those that will be carrying 4, horizontal column 4. For example, looking at these 2 examples of ours, calling them element A and element B, for us to locate A in this table, we shall have A, check, since they are of the same reaction properties, let's assume their properties will be placed in number 2. So we place them in number 2, so they will all lie in this vertical line, vertical column number 2, because their characteristics are agreeing with maybe vertical column 2. Then we look at the number of electrons in the outermost energy level. There are 2 here, so we shall have our A here, and here there are 4 because this is 1, 2, 3, and 4. So B will be at that position. But remember, they are having similar way of reaction, therefore we categorize them in the same group. This gives us 2 things in a periodic table. One, I've already given the name, but not directly. So giving the name directly is the vertical columns in a periodic table are called groups. So vertical groups. Then we also have horizontal. Horizontal are periods. We have horizontal which are periods. Only the 2. We either talk about a group or we talk about periods. Where is the difference? For groups, we look at properties. We look at properties. Those elements that have similar properties, similar chemical characteristics, similar properties, similar chemical characteristics are categorized under the same vertical column, which we are calling now a group. Later on, you will also go further and discover that in some books, they are even using other words like a family, a chemical family. Instead of calling it a group, you can also call it a chemical family, because if you are members of a family, it means you are members that are sharing some kind of characteristics. It can be physical characteristics by appearance. Maybe you are all tall, you are all maybe light-skinned, and so on. But you will be sharing some characteristics. So they can as well be called families, but being that there are chemicals, we call them then chemical families, not just families as we call ourselves, for example, human beings and other animals. That is in the vertical, we look at properties. Then in the horizontal, which we are calling a period, we look at number of electrons. Number of electrons. Number of electrons. This number of electrons is particularly only to the outermost orbit line or outermost energy level. You don't look at the other orbits. You only look at the outermost orbit. Now, I have here a copy of the periodic table, a full periodic table, which after all the work starting from what Mendeleev did up to what is being done up to today, because so much work in science is always going on. Things are being improved on day in, day out. So at now, this is the present periodic table we have, which has so many elements in it. You remember in our previous lessons, there's a lesson where I indicated the number of the elements that are existing. But out of that, 92 are the ones that can naturally be found. The others, so as you can see, we are talking about so many elements. Now, looking at this table, let's relate what I've just mentioned from the table I've drawn and the table I'm having on this paper, which we are calling a periodic table. In this periodic table, we have the columns that are going vertically, so many of them. Then we also have those that are going horizontal. Then we also have these other elements down here. Maybe let's get them by numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 times 2, 30. These elements do not just occur easily. They are called the rare earth metals. You will find that they are very important in some cases, very important. They will be found in so many electronic equipments, very sensitive electronic equipments being used in such electronic equipments, doing very sensitive work, like in surgery work and so on, but they are rare in terms of occurrence. We also have those that rarely exist for long. They exist for a short period and they disappear. But we cannot say that they are not there. They are there. It's only that they, what we call half-life, you learn it in later lessons. We also have what we call decay of elements. So those that have a very short, what we call half-life, will always appear for a short period and disappear. But all in all, they are included in the periodic table. Now, let's look at this periodic table and try to understand why it has been colored the way it is before looking at the details of each of the element and the numbers that are appearing in the table. Because as you can see, we have numbers in that table. But before we look at those numbers, let's understand why this table has been colored the way it is. Does it have any significance? And the answer here is yes. Looking at the first column, we have two colors. And it is in addition to this one, the only ones that are having two colors in one column. This shows some special aspect of that element that is carrying a different color from the others. So starting with the first one, where we are having a yellow and a green on top. The one that is in green is by the name hydrogen. And the ones that are at the bottom, we have an example of lithium, sodium, potassium, rubidium, cesium, and francium. These are elements that lie in the same group, vertical, same group. Why? They have the same properties. They have the same chemical characteristics, which we call, therefore, by a chemical family name, alkali metals. They are called alkali metals. So the family name to this group of elements is alkali metals. But remember, the name does not include the first element, hydrogen. And as you can see, the green color is differentiating it from these others. That's why even if it is found in group 1, it does not carry the group name or the family name as alkali metals. Then the question comes, why is it that it is different and it is put in the same group as the alkali metals? One of the characteristics that this family is having is the number of electrons on the outermost orbit line or outermost energy level. Starting from lithium, sodium, if I can just use these three, they all have 1 electron in their outermost orbit. Just like hydrogen, which also has 1. So because of having 1 electron in each case, then, and it is this one that gives them their chemical properties. It is this having 1 electron in their outermost energy level or outermost orbit that gives them their chemical property. Then it qualifies hydrogen also to be found in that group. However, being a non-metal, though with the same characteristics because of the 1, it has to be special and it must be indicated. So hydrogen is a non-metal. That's why it is sharing the color with the non-metals that are in green. So the ones that are in green are non-metals, and the ones that are here in yellow are not the only metals, but they are metals, but special metals in group number 1 called alkali metals. The second vertical column is another set of metals that have the outermost energy level or orbit having 2 electrons. They are having 2 electrons. An example here is magnesium. I can use only 3 examples here. We can have beryllium, magnesium, and calcium. They are all having 2 electrons in their outermost energy level. Having that 2, and it is that 2 that makes them to behave in the same way, to have the same chemical characteristics, chemical properties. Because of the same properties, they are put in the same group. And that group is called alkaline earth metals. Alkaline earth metals. Now I need to comment on this name. You will find that in some books, like where I got this table, you find they use, instead of alkaline, they use the word alkali. This one was changed, and that's why I had to come up with this, because probably you may get a book that is using this information. Alkali comes from the word alkyl, which means ash producing, producing. So in ash producing, you discover that when you burn wood, much of the metal that will be found in the wood will be sodium and potassium. So it is only that compound that contains sodium and potassium that now qualifies to use the word alkali, A-L-I, without N-E. But now, looking at magnesium and calcium specifically, these are compounds that on reacting, they form compounds that when you dissolve in water, they form alkaline solutions. Alkaline solutions. In addition to that, when you look at the Earth's crust, they form a bigger part of the Earth's crust. And because of that, forming the Earth and also forming an alkaline solution, combining the two gave now the name alkaline earth metals. This is the correct name, not alkali earth metals. Alkaline earth metals. Why? They all have 2 electrons in their outermost energy level. Then after that, we have another set which is now the biggest in the table, as you can see, is the biggest. And this one is what we call transition metals. Transition metals. It is the biggest and it has so many of them. Most of the metals we are interacting with are partly here, but some are not here. Some of these are special metals which are used in special places, but all in all they are called transition metals. They are metals. So this one gives us a category of now how many metals? 1 category, which is first group. Second category, alkaline earth metals. Third category, what we are calling transition metals. And now we are left with a 4th category, which is a special one, that is starting with the aluminium. We have germanium, gallium, tin, and so on. When you have a piece of the periodic table, you can get all of them. But starting with the aluminium, these are metals that have very unique characteristics. These are metals that at one point you know them to be metals, but they will start behaving like they are non-metals, especially when they are in compound form with the particular elements. For example, when aluminium is combined with the chlorine, you will find that it will be giving a very unique characteristic of being a compound that undergoes sublimation. It is a compound that exists in a gaseous state. And yet, aluminium chloride, if you pick a metal like sodium and magnesium and you form a chloride of the same, that is sodium chloride or magnesium chloride, you find that the characteristics are totally different. Aluminium chloride is existing as a molecule, taking a behavior of a nanometal, and yet aluminium is a metal. Looking at germanium and gallium, these are metals that are used in as semimetals, semiconductors. They are used as semiconductors, meaning that at one point it's like it doesn't want to conduct, but another point it wants to conduct. And what we know, there are nanometals that do not conduct. Metals conduct. So they are behaving at one point like metals and others are as nanometals, but in general they are metals. In general, they are metals. Never categorize them as nanometals. So we have 4 categories of metals. Then let's look at nanometals, starting with the special one that is having a share in the first group, and that is the ones that shaded in green. We have here hydrogen, then we have boron, carbon, nitrogen, phosphorus, sulfur, and so on. If you have a copy, you can get all those. So these are nanometals, but we also have another category of nanometals that have been categorized differently, put in a different group from these ones, and that is halogens. The halogens, they are nanometals, but special nanometals, specifically called halogens. Why are they categorized specially? You can see they are the only nanometals that are moving straight in a column. These are nanometals that have special characteristic. These are nanometals that when you look at the outermost energy level or the outermost orbit, they are missing only one electron to fill up the orbit. Depending on which orbit you are talking about, you only miss one electron, and there you are full. So these nanometals that are missing one electron to be full are generally called halogens. Very special indeed in terms of reaction, and in fact, in terms of reactivity, they are the most reactive nanometals, going by each period. Depending on which period you are talking about, the halogens are usually the most reactive nanometals. Then lastly, on the upper part, we are having another column which is including helium, neon, argon, krypton, xenon, and rubidium. Now these ones are elements that do not undergo chemical reactions. These are elements that do not undergo chemical reactions. Why? These are elements that do not undergo chemical reactions. We have to ask ourselves why. Because all the others can take part in a chemical reactions or reaction. But this one, this category of or a group of elements do not undergo chemical reactions. The answer lies in why do elements undergo chemical reactions? That's where the answer lies. All elements react to look for stability. Stability means the outermost orbit or the outermost energy level should be full. Just like when you are hungry. Being hungry, it means your stomach is empty. But it might be having something small in it, but still you will not be comfortable. But once you have a meal, your stomach is full, you are comfortable. If you are maybe moving around aimlessly, you will now go somewhere, sit calmly, you are comfortable, you are stable. So just like what I've described in terms of when you are hungry, these elements also have that case, stability. But remember, stability can also be, if I can go back to the issue of food again, you have just had a meal, but you have eaten excess. You have eaten excess. For you to be comfortable, part of the food must go out until you go to where you are supposed to be, the stable point. Otherwise, you will be unstable. The other case is, maybe you have some food, but not enough. You will still not be stable. But if you add in some food until you reach where you are supposed to reach, you will be stable. Elements also behave the same way. So, when the elements want to be full, you have an element that has an outermost energy level having 2. But the target is to have 8. So it has 2, but the target is to have 8. You have another element that is having 6. It is having 6, but the target is 8. These elements, remember, in losing or gaining electrons, you require energy. So the elements will always look for the best route to get the outermost being 8. The outermost being 8, but using the minimum energy possible. So remember, These elements will also be having innermost energy levels, which might be having 8. Like now, in this case, if I can have 1, 2, 3, 4, 5, 6, 7, 8. The innermost is having 8. We can also have this one having 8. 1, 2, 3, 4, 5, 6, 7, 8. The innermost is also having 8. But we are not interested in the innermost. We are interested in the outermost. It is the one that is involved in chemical reaction, and is the one that is being used to categorize them into various chemical families, different chemical characteristics. Now, in our first case, case 1 and case 2, which one will be the shortest route? Is it to lose these two so that you can remain with the innermost as the outermost, remain with the innermost as the outermost, and being the outermost, it will now be having 8, or gain 6 or gain 6 so that the outermost will now have 8. In gaining 6 and in losing 2, you will require less energy than in gaining 6. So logic has is that you will obviously go for losing the 2 and not gaining the 6. But let's look at case number 2. Outermost has 6. It requires 2. A plus of 2, then you are at 8. Or lose the 6. Lose the 6 so that you can have the innermost as the outermost. As I've said, losing and gaining, whether you are losing or gaining, if you are talking about 1 electron, the energy is the same. The energy you will use in losing 1 electron is the same energy you will use in gaining 1 electron. So this one will be 3 times this one. Logic has that you better gain the 2 electrons so that you can reach at 8. So all these now gives us on how all these behave. All these other elements, we have talked about metals or non-metals, but the other elements we have talked about how they react. But now we are talking about the last group, the last chemical family. They have similar characteristics, and the similar characteristic is that the outermost energy level is full. It has 8. 1, 2, 3, 4, 5, 6, 7, 8. So it has 8. And it requires 8. Does it have to lose or gain? No. So all these elements do not undergo reaction. All these elements do not undergo reaction, and therefore they are called inert elements. The name of the word inert means unreactive. Inert, unreactive. So these are unreactive elements. These are inert elements. Then down there in the purple, we have what I had mentioned earlier. We counted, in fact, and we saw there are 30 of them, and there are the rare earth metals. They are found in the earth, but rarely will you find them. And when you find them, some of them are very, very expensive. Very expensive indeed, because of particularly their uses in whichever places they are normally used. Like now, if you look at the one carrying 92 as atomic number and mass 238, that is the uranium. When you are talking about energy production here on Earth, you find that is a very interesting topic, energy production, because in everything that we do, we require energy, electrical energy, in particular, electrical energy, which is being used to power so many things around us. So you find that we shall never have enough energy. But we have always to look for ways to improve on how much energy we are producing. So you find that the best improvement human beings have come up with is nuclear energy. Nuclear energy. So in the nuclear energy, the compound, the element, the substances that are used in the nuclear energy, one of it is uranium. Uranium is unstable. It easily decays, decomposes, and when it does that, it produces a lot of energy, something that we shall discuss later on in nuclear, in radioactive decay, when we shall be talking about the various elements and what happens when we are talking about radioactive, half-life, and the rest. So you find that because of such uses, you don't just get uranium, it's expensive, and even if you have to get it, you have to get it in a special way. It is not just an element you can handle in any other manner, just like you can handle these others like iron, zinc, and the rest. This one must be handled with a lot of care, with a lot of knowledge, because of how it exists and how it behaves. So how do they behave? They easily undergo decay. They disintegrate. And when they disintegrate, they give out energy, a lot of energy. And part of this energy can be very much harmful to us because it can cause things we call mutation, gene mutation. In the biological part of science, if you haven't covered, you will be covering, where you find that we are decoded in terms of genes, and those genes can be interfered with, what we call mutation. So when you interfere with the gene, it means you are interfering with the way you look. So that's why you will find that some people may be born with some deformations, and those deformations are not just malfunctions maybe in the development, but it's because of mutation. These are cases like what happened in Japan when during the World War, where an atomic bomb was used, and after being used, you find that some of the human beings and even animals that were being born, and even plants, were carrying unique characteristics, which was because of the type of effect you can get when you are exposed to this. So that is all about looking at the various categories of this periodic table. I want us now to look at another aspect, which is to look at why has each of these elements been written in the way it has been written. It must be having a reason why it has been written the way it is. So just taking the key as it has been indicated up here. So up here we are having a key, an example, they are picking on gold. Gold is written as capital letter A, small letter U. So this is the chemical symbol for gold. Now, if I want to pick out where gold is found in this table, if I want to pick out where gold is in this table, I have to know the interpretation of these numbers. There's a number that has been written on top, and that is 79. There's another number written down here as 197.0. So we need to know or interpret the numbers first. And these numbers will assist us understand the locality of these elements in the table. The first number, 79, is the atomic number. Atomic number. What is atomic number? Atomic number is the same as number of protons. Number of protons in the nucleus. So when you are talking about number of protons, in one way or another, you are just talking about the atomic number, which is written on top here. In some periodic tables, you will find that it has been, these numbers are not written the way they are written in this format, we need also to know this. You'll find that some periodic tables will have the big number, which is the mass number 197 on top, and atomic number at the bottom, but now sideways, not on top and at the bottom as the case we have just seen for this one. So in whichever way, the small number you will always be seeing is the atomic number. The small number you will always be seeing is the atomic number or the number of protons, and the big number you will always be seeing irrespective of the periodic table you may get and the position. It will be meaning the, so this one was atomic number, and this one is mass number. Mass number. Now what is mass number? Mass number, when Mendeleev was trying to rearrange these elements, he was using mass, but he didn't know that this mass is being contributed by two things. But in 1932, when James Chadwick came in, he now discovered that the other subatomic particle that is contributing to mass in addition to protons is neutrons. So we have mass number, the big number, which is a total of protons and neutrons. Protons and neutrons as in a total. Then you get mass number. Now, for you to use these numbers to locate an element, you have to go for atomic numbers. Atomic numbers. Why atomic number? In any atom, the number of protons, because atomic number is the same as number of protons, the number of protons, is equal to number of electrons. Is equal to number of electrons. This is very important for any neutral atom that hasn't undergone any chemical reaction. Number of protons is equal to number of electrons. Why is it important? It is important because for us to arrange them in the columns and in the periods, that is in the groups and the periods, electrons are used. Electrons are used in what we call electronic configuration. That's why, if you can remember, I said that for you to place elements in periods, you look at the number of electrons in the outermost energy level, electrons. Number of electrons in the outermost energy level or outermost orbit. We are checking on the number of electrons. So these ones will give us all the arrangement until you get where the atom is, the element is found in the table. So looking at this table, let's see if we can identify where gold is. Being atomic number 79, you directly go to 79 and this is the point. It is found under category of transition metals. Gold is found under transition metals and it has an atomic number of 79 and mass number of 197. Now, having looked at the periodic table, having looked at the explanation bit of it, why maybe a certain element is found here and not there, for us to see whether we have gotten the concept or not, we have understood what the table is talking about or not, let's try to answer a few questions that will assess ourselves to see if we have gotten the point as supposed. So I will be giving out questions and alternatives. Then you pick out the correct alternative. First question. What is the atomic number of magnesium? What is the atomic number of magnesium? What is the atomic number of magnesium? Is it 4, 12, 25, or 42? Now, if you have this table, you can reduce this table to a smaller one for maybe easier practice. Instead of working with the big one, you can reduce it to a smaller one where you will now pull out the transition metals so that you remain with these other, which are 1, 2, 3, 4, 5, 6, 7, 8. And that is where the number 8 came from. They always assume the transition metals. So for us to answer this question, I would like us to use this table. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. When writing groups, we use this format: 1, 2, 3, 4, 5, 6, 7, then lastly 8. And when writing periods, we use the format 1, 2, 3, 4, 5. Or you can as well write 5 this way, either of the two. Now, when we have magnesium, I'm going to give the answer to this so that it can give us now a way on how to get the others. So when I have magnesium here has 12 protons. Magnesium has 12 protons. And I said the number of protons, or the atomic number, is equal to the number of electrons. So if the number of electrons for this magnesium is the same as the number of protons, then it means we are talking about 12 electrons. When we write the electronic configuration, there are rules we have to follow. The first orbit carries a maximum of 2 electrons because it is small. Carries a maximum of 2 electrons. Remember, we are narrowing ourselves to a smaller periodic table. For us to understand the big one, the way to explain will be a bit different from the small one. The big one, we shall look at it differently. But for now, let's look at the small part of the periodic table. The first orbit, 2. The second orbit, 8. The third orbit, 8. And we shall work with only these ones. For the fourth one, it is a bit special, and that's the part I'm saying. For us to understand, we shall require some other additional information for us to understand how all of them are arranged. But for the first ones, we can get it very easily the way we are going to do it. So let's arrange these electrons in this order following a maximum of 12. So for magnesium, the first energy level or orbit has a maximum of 2. So we subtract here 2. We are remaining with 10. So we can comfortably go for another 8 because we haven't covered the remaining 10. So if we out of the 10, we get now out 8. How many are remaining? 2. So we go to the next orbit, which is now a maximum of 2. So that the 3 put together will total to 12. 2 plus 8 plus 2 gives us 12. Now, where do we get the group and where do we get the period? Because here we are talking about group and here we are talking about the period. How do we get the period and how do we get the group? The group is the outermost. The group is the number of the outermost orbit. So we shall have it in group number 2, this one. Then the period is the number of energy levels, and that is 2, 8, 2. How many? So we have one energy level, the second energy level, the third energy level. So it is in the third energy level and in the second group. So meaning that this is where magnesium is supposed to be. So looking at this periodic table, you will go try and see, can you find this one fitting in this one? Minus the blue region, which is the transition metals. Do this, remove the transition metals, take this one and fit to this one. Will it agree with this? The answer will be yes, so long as we follow this. So answering the question, what is the atomic number of the magnesium? You just look at the locality. Once you identify the locality, then look at how many energy levels, how many electrons in the outermost energy level, and you are good to go to identify the number. Let's look at one element which will give us a direction, then you go and work on the others so that we can continue in our next lesson. So let's look at an element like which element has atomic number 15? Which element has atomic number 15? Element that has atomic number 15. What do? Ask yourself, any relationship between atomic number and number of electrons? Yes, it is there. Atomic number is the same as number of protons, and number of protons is the same as number of electrons, and the number of electrons we are having here is 15. So once you get this, you now write what we call electronic configuration. Let's do it. 2, remaining 13, 8, remaining 5, 5, all the 15. So 2 plus 8 plus 5, we get 15. Let's now identify which element is in this position. Which element is in this position? Let's start with the group. The group is this one. That is group number 5, because it has 5 electrons in the outermost orbit. 1, 2, 3, 4, 5. So it is at that point. Let's identify the number of periods. 1, 2, 3. So it is in this period. Let's now move. 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 We meet here. So the element that will be at that position is the one that is having atomic number 15. And what is that element? If I look at this, 3 is this one. This 3, because we have 3 is this one. 1, 2, 3. So 3 is at this point. Then we are pushing out the transition metals. So we look at the outermost 5. We have 1, 2, 3, 4, 5. That is the point. So we have 1, 2, 3, 4, 5. 1, 2, 3. 3, 5. Let's move. You move to 5, and that is the point. And the element is phosphorus. So here at point X, the element is phosphorus. That is how the periodic table was constructed, and we are happily using it with a lot of ease, making our life in science very easy. So I give you a challenge of going at your own pace time. Try to fill in this table. In our next lesson, we shall revisit it and see what you will have done. That marks the end of our lesson today. Thank you.